Hi everyone, today we're going to discuss the last topic in chapter 3, which is Euler Diagrams and Syllogistic Arguments. Syllogism is just another form of an argument, and we're going to determine whether the argument's valid or invalid using something called an Euler diagram. So Euler was a mathematician, and I discuss a little bit about him. He was born in 1707 and he died in 1783, and he developed this method that's a visual method for showing whether a syllogism is valid or not. Syllogistic logic is a deductive process, so we start with something general and arrive at a more specific conclusion. So, deductive reasoning is used if you go to the doctors and you tell them, what's wrong with you. Like if you say, I have a sore throat, that could be a lot of things. So that's a very general statement. The doctor needs to use deductive reasoning to figure out specifically what's wrong with you. So that's kind of what we do with syllogisms, is we start with something general and then work our way down to something more specific to arrive at a conclusion. We're going to look at the words all are, no are, some are, and some are not. So in previous sections, when we were looking at and or, the word not, if then, and if and only if, we used truth tables to compare and determine the truth value of the statements. For our syllogisms, when we're looking at all, no, some are, and some are not, we're instead going to determine whether the statements are valid by constructing an Euler diagram. As we discussed before, an argument's valid when the conclusion follows from a given set of premises. And an argument in which the conclusion does not follow from the premises is said to be invalid, and we also call that a fallacy. Before, we looked at Venn diagrams to look at sets, and we also used them to look at some visual displays of logic. So here's 4 Venn diagrams that discuss the quantifiers all, no, and some are not. So when we say all A's are B's, as you can see here, you've got your universal set, which is the rectangle, and then you've got 2 circles, A and B, and A has a square inside of it. So because all of A is inside of B, that means all A's are B's. If you'll remember back in chapter 2, this was kind of like a subset. So we would say that A is a subset of B because all of A is a part of B. In the second diagram, you've got 2 circles that don't intersect at all. So if you remember back in chapter 2, we called those disjoint, which is also mutually exclusive. It's when no events are in common. So there's no intersection there. In the third, we've got an intersection right in the middle. And if you'll recall back in chapter 2, that would be where we would say A intersects B. So some A's are B's. But if you look at the last diagram, some A's are not B's. So we're talking about this piece right in here because that's just A. Or you could even say A only. So we're going to construct some Euler diagrams using those 4 Venn diagrams as a reference. So let's look at our first example here. It says determine whether the following syllogism is valid or invalid. So we've got our premise 1 and our premise 2, and then we have our conclusion in the very last statement. So do these premises, do they lead to the conclusion? It says all keys are made of brass and all things made of brass are valuable. So all keys are valuable. So first I want to go through here and figure out, okay, how many circles will I need? So one of them talks about keys, all keys. Another one talks about all things made of brass. And then it mentions about things being valuable. So I'm going to need to have 3 circles. And I'm using the word all. So when I construct my Euler diagram, I'm going to have my rectangle for my universal set. So I'm going to put a U here. And we're going to kind of work inwards to outwards. So it says all keys are made of brass. So that means for my brass circle, I'm going to have a key circle inside because all keys are inside the brass circle. So if you look at that visually, that tells us all keys are brass. And what do we know about all things made of brass? They are valuable. So I have to put a circle around the brass with the V for valuable. Since all the keys are within the valuable circle, which is what my conclusion says, it says all keys are valuable, then it follows that the conclusion is a valid statement. It's a true statement because all keys are valuable since the key circle is inside the valuable circle, which is the entire circle here. Excuse me. So this is a valid statement. Is the conclusion all keys are valuable a true statement? Yes. So one of the things to remember is that the form of the argument determines its validity, not the particular statements. So what do I mean by that? Okay, if we look at our first example here, it says this argument is valid as the form is the same as the previous argument. Okay, so if I go back to my argument here, let's talk about form for a second. So I've got all keys are made of brass, right? So I'm going to write something like this. All keys are made of brass. And then it says all things made of brass are valuable. So what was my conclusion? All keys are valuable. So the way I look at it is I notice that in my 2 premises, I've got the B's there. What's left over? A K and a V. What do you have in your conclusion? A K and a V. So that means that the conclusion's valid. Let's see if the same one follows. This argument here follows the same format. So it says all Earth people, so I'll just do P for people, have 2 heads. And all people that have 2 heads can fly. Therefore, all people can fly. So let's see if the same occurs. I have 2 heads here repeated, and what's left over? P and F, which is what I have in my conclusion. So again, this is valid. It has the same form as what is above. So the form of the argument determines the validity, not the particular statements. Okay, try to pause the video and examine the last 2 examples, A and B, and determine whether the following syllogisms are valid or invalid. and then unpause when you're ready to return and find out the answer. So for example A, it says all knights are athletes. Brett is a knight, therefore Brett is an athlete. Okay, let's draw a picture of what that would look like first, and then we'll talk about whether it's valid. So I've got my universal, and it says all knights are athletes. Okay, so all knights are athletes. So I need a circle for knights, and then all knights are athletes. I need a circle for athletes. Brett is a knight, so Brett's going to go inside here. And I'll put a little circle there. Therefore, Brett is an athlete. Okay, so let's see if that's the same form as before. So I've got all knights are athletes. Brett is a knight. Therefore, Brett is an athlete. So I've got my two repeated, and here I have an A and a B. And this tells us also we've got an A and a B. So therefore, this is a valid conclusion. In the last one, we've got no fish are mammals, all cows are mammals, and therefore no fish are cows. So you might want to refer back to one of these diagrams in the previous page. So we're dealing with the word no. So I'm going to focus on this one right here. So I've got my universal set, and it says no fish are mammals. So when I draw a circle for fish and a circle for mammals, they're going to not intersect. They're going to be disjoint because no fish are mammals. All cows are mammals. Okay, so cows is going to go in this circle, just like Brett went in the knight circle above. Is this a valid statement? So it says no fish are cows. So since the fish circle doesn't at all intersect with the mammal circle, which is where cows are, it's a valid statement again. So one thing to remember here, it doesn't say the conclusion is true. It's just saying that the argument is valid. So I'm going to put a little note here to remember. Okay, that concludes section 3.6, and there is no homework on my lab for 3.6, but please make sure that you concentrate on the test review for preparation for the test. All right, I hope you all enjoy the rest of your day. If you have any questions, please don't hesitate to contact me in the meantime.